Well, we did right. They well, it's very he directed case maker, maybe to change the light. I think he was trying to
all right. Okay. So the test is Friday, and the questions are going to be resembling, little things will be changed, but resembling the review set problems that you have, as well as maybe something from the take-home quiz, which is also due on Friday. The solutions to that review set are posted on Blackboard. And then the homework that you've all been delivered, that's going to be due the following week. For your Rockwood students, you could either turn that in on Wednesday or the following Monday, since you're off on Friday the 18th. Also, just I'll be to Jerry, and I'm hand delivering I just sent you an email. I'll be delivering the test over to your Welcome Center after the class. Okay. So, a lot of different sections here. And what I'd like to do is I actually look through the review set and pick some that I thought would be good to go over. But certainly if there's anything that's coming to mind that is a pressing question, we can also entertain that. And that also can be concerning the take-home quiz, which is due on Friday. All right. So you can think about that. If you don't immediately come up with something, you can, perhaps if you come up with something during class, that's fine. Just let me know. And that, of course, applies to you guys out there. So before I kind of start with going through some things, are there any additional concerns about the take-home quiz? Number 6, confused about how to get the bound. Okay, let's see. Here's number 6. Using polar coordinates to find the volume. Okay, so the volume's trapped inside of a cylinder, and it's also in an ellipsoid. Okay, all right. Now, what we have here, this ellipsoid kind of looks like a sphere, except it's kind of an oblong sphere. All right, that's what an ellipsoid is. So basically, let's look at this break down this ellipsoid thing like this, here, let's put this paper here, it's z squared, I'm isolating the z squared on one side, so it's z squared, and I have it right here, is equal to 64 minus 4x squared minus 4y squared. So if I do the square root of both sides, I then have z is equal to plus or minus the square root of 64 minus 4x squared minus 4y squared, like that, all right? So the plus would be my upper, what I call my upper z. The minus here would be what I call my lower z, all right? Okay. And then, okay, what we then have to look at here is, all right, we're going to be doing this with polar coordinates because everything screams out polar coordinates because it's x squared and y squared. What we're going to be integrating here over some region is we're going to take the upper z minus the lower z, and of course, when you do that, you have a double negative here, so you basically end up integrating 2 times that square root of 64 minus 4x squared minus 4y squared. When you subtract the negative, all right, you have 2 of them. And then you have to figure out this region D. Now, and in fact, I give you that right here. The region D is, remember, it's trapped inside the cylinder. So the region D on the XY plane is going to be that circle. And what's the radius of the circle going to be, or the disk going to be? The radius is going to be 2. All right. So this is basically how you set it up. You're going to have, and it's going all the way around, so it's 0 to 2 pi for theta. R is going from 0 to 2. And then you have this. Now, I need to represent that in terms of polar coordinates, right? So how can I take this right here and represent it in polar coordinates? Yeah, Jordan? Okay, 2 times the square root of 64 minus 4r squared. And then notice also, if you want to do an additional simplification with this, I can take a 4 out of both of those terms under the square root, right? So this can be, so I take a 4 out, that'll give me a 2. So that's 4 times, 16 minus r squared, I believe. Is that right? Yeah. 2 times 2, yeah, that should be right. So this is what we have. And then what now do I, and then I'll stop with this, then what do I add on here? I'm not quite finished with my integral. R dr d theta, and we're able to do that integration and get our answer. But that's how you need to set that up. This is number 6 on the take-home quiz. Did that help? Okay. Anything else that's coming up? Yeah, Tom?
On number 7, so it looks like we have on the board.
Yes, number 7.
Does it go from 0 to pi at this, or would it be?
Well, let's see here what it would go from. This is number. Let's check it out. So Tom has a question here about number 7. Jenna, I'll give you this piece of paper, okay? All right. I know. Well, you took a picture of the board. I know, but so it's asking us to evaluate this double integral by going to polar coordinates, and I do give you a couple of hints here. The y limits are from 0 to the square root of 2x minus x squared. So the y goes from 0 to the square root of 2x minus x squared. So let's look at this. This is our upper limit for y. Let's check this out and see what more information we can get from this. Let's set y equal to this upper limit and square both sides. So we get y squared is equal to 2x minus x squared. And then notice we have a y squared, we have an x squared, so hopefully you would think you want to get those together to get hopefully an r squared, right? So we have y squared plus x squared is equal to 2x. So now we can put this in terms of polar coordinates, and y squared plus x squared we know is equal to r squared, and 2x is 2 times r cosine of theta. And then we're assuming here with our upper limit that r doesn't equal 0, so we'll divide by r, and we get that r is equal to 2 cosine of theta. This is our upper limit for r. So when we integrate this, r is going to be going from 0 to 2 cosine of theta. Now let's look at this 2 cosine of theta business here. And let's do a little table and make sure that we're on the right path. Same here. Okay, when theta is equal to 0, then of course 2 cosine of theta is going to equal 2 times 1. So it's 2. And let's then look at pi over 2, 90 degrees. So when it's pi over 2, yeah, I think you're right there. When it's pi over 2, we have 2 times 0, so we have 0. So this point right here represents when theta is equal to pi over 2. So going from here, it is a circle going from here to here is 0 to pi over 2. Right. But let's see what happens. Let's skip down. What happens when theta is equal to pi? When theta is equal to pi, we have what? 2 times the cosine of pi, which is, cosine of pi is -1, right? So we have -2. Actually, the point, let's see, we always put the r first, r comma theta, right? -2 comma pi, that in polar coordinates is actually going to be, because the angle pi is here, but because r is -2, that would be here. So that also represents theta equaling pi. So yes, the limit of integration then, and change that then, is, you were correct the first time, was 0 to, for theta then, thanks Tom, goes from 0 to pi over 2. All right. And then you can just finish the problem. You've got your limits of integration. You convert everything to polar coordinates, and you should be fine with that problem. Okay. Because look at what we're integrating. We're integrating the square root of x squared plus y squared, which is just going to be r. All right. Okay. Anything else on the take-home quiz? Yeah, wait a minute, I think we're on.
You were talking about complete circuit equation circle. Why did you do that?
Okay, the reason I did that was I wanted to just see. I just wanted to get an idea of what this thing looks like. So rather than immediately go to polar coordinates. So what I meant by that was something like this. Okay, here's our upper limit is this thing right here. When I squared both sides, I got y squared. I'm sorry, let's go with this one. let's go with a new piece of paper, huh? Basically, we get this. X squared minus 2x plus y squared equal to 0. And this is going to be a circle. So I just wanted, just so that you had an idea of what it is that y is, that this upper function is here. So I just complete the square in terms of x. We divide the minus 2 by 2, we get minus 1, and we square the minus 1 to get 1. So this becomes x minus 1 squared plus y squared, and then of course I have to add the 1 over onto the right-hand side. So I just wanted, so you can see hopefully readily that this is a circle, radius 1, and its center is 1, 0. All right. But this circle is the same thing, Jordan, as 2r equals 2 times the cosine of theta. All right. R equals 2 cosine of theta is that, we have just seen that here, right here. Where, oh, here. It turns out to be a circle of radius, right here, it's a circle, except in this case, we're only looking at the upper half of the circle because we're told that the lower limit for y is 0. So we're only looking at the upper half.
Yeah, but then how do you get, if we're doing like square, or how do you get the whole integration for theta?
Now, then that's the whole process I did there.
I mean, kind of like going by the circle equation, not the our using those theta.
Okay.
Because I just found like from the end, I assumed it was from 0 to pi.
Right, and it is just as we had seen here, that half circle is only just 0 to pi over 2.
No, 0 to pi.
Yeah, right.
Not 0 to pi over 2.
Mm-hmm. But do you understand why it's just 0 to pi over 2?
Not going by the hand, or square.
All right, okay. I tell you what, just ignore the hint about completing the square then. The only reason I added that in there is that you get an idea of how y, that upper limit for y is actually a half circle. In rectangular coordinates, it's a half circle.
I mean, I know it's a half circle, that way, when it's a half circle, it wouldn't be going from 0 to pi. I'm not sure.
Well, it's not, you're right, it's not, okay, if it were a half circle like this, centered on the origin, okay, then, which is, say, r equals cosine of theta, then it would go from 0 to pi. But we just saw by looking at this table that pi over 2 completes the other end of that half circle. So you stop there. And it's only by completing the, I understand why you would think, because that's what I thought at first too, that it would be pi, because it's on the other end of 0. But in this case, it will just be pi over 2 if you do the table. Yes. It becomes 8 cosine cubed.
Over 3.
Now, I'm not going to do this, but let's look at 8 cosine cubed over 3. Now, how would I approach that? Somebody help me out here.
What do you want to do, square?
Yeah. Cosine cubed can be broken apart as cosine times cosine squared. And then what do I replace cosine squared with? It's 1 minus sine squared, not sine squared minus 1 minus sine squared. And then I do, so what I have here for cosine cubed is cosine minus, when I distribute, is cosine minus cosine times sine squared. And Jenna is stating that at the end of the problem, of this problem, you end up having to integrate h cosine cubed over 3. I mean, that's what she says. I'm not verifying that that is true or not, but her question was, how do I integrate cosine cubed? Do you see how you do that now?
Yeah, but when I square
No. What technique learned in Calc 1 do you use to help with this? U substitution. Let u equal the sine. du is going to be the cosine d theta. All right? You do a u substitution.
I don't understand how we got
I don't know either because that's what she's saying. All right? You're getting something different. Well, maybe we're getting something different. Let's see here. Do I have? Yes, of course. You have the first term, which is just a cosine. Second term, you're going to use the u substitution. Yeah, that's what I get. I'm seeing that, so it is correct that when you get to the bottom of this problem, it is h cosine cubed over 3, and the limits of integration are 0 to pi over 2. That is the tail end of this problem.
I understand, because wouldn't the period of x versus y versus r?
Mm-hmm. You know what you're missing? You're missing adding on so that is r. But what you missed is r d theta. Did you add that extra r in?
Yeah.
R squared. And what do you get when you integrate r squared?
R cubed over 3.
Yeah. Mm-hmm. That's where the cube over 3 comes from.
Then where's the h cosine?
Because what are our limits of integration here? I just had given you that the upper limit of integration for your r is going to be 2 cosine of theta.
Why would we plug h cosine d for r for 3 by r?
2 cubed is 8.
2 cubed is 8. Cosine cubed is cosine cubed.
Why would we plug that in the first place? If we're going to go to by r, we wouldn't need any plug-in cosine from r.
Wait a minute. Hold it. I might as well just do the whole problem. All right? We just might as well do the whole problem. I'll be nice. 0 to pi over 2. R goes from 0 to 2 cosine of theta. We're integrating r, and then we add the r d theta. This, of course, is r squared. We're integrating r squared. That's r to the 3 over 3. I have to then apply my limits of integration. 0 to 2 cosine of theta. That gives me what?
Oh, I guess look at this wrong. How is the limit of integration going from 0 to cosine theta? Is it the radius wouldn't be 0 to 1?
You are treating it like a circle that has its center on the origin. This circle, half circle, is off kilter. It has its center at 1, 0. I had gone through the process earlier of showing why the upper limit of integration for r is 2 cosine of theta by converting this upper limit for y into polar coordinates. I squared both sides, got y squared plus x squared on one side, replaced all this with polar coordinates, divided by r since we had an r on both sides, and came up with my upper limit for r is 2 cosine of theta, not 1. If you draw this diagram correctly here, you would see, that will then reinforce the fact that the upper limit for r is going from 0 here at the origin to 2 cosine of theta. I'll talk with you after class more. I'm not going to go further on this question. Okay, anything? Yes.
For number 2, there's S times Y times B less or Y. I'm kind of like having trouble figuring out how to integrate that.
Oh.
So we had a problem like that somewhere on the,
Mm-hmm.
on the
Well, all right. Okay, so tell me give me the iterated integral that you first set up.
The first one is 0.
This is number 2. Go on.
I have the first one is 0 to 1.
Okay, so you're integrating, so your outer limit is the dx then. Okay.
And then 0 to 2.
0 to 2, so your inner one is dy, all right? And then you have xy e x squared y. Okay. Okay. So let's see. So if you do it this way, let's see, because I integrated in the other order here. This means that x is considered a constant, right? Okay. So therefore, when you do the integration here, you're making life hard. This is the hard way. All right. But let's just look at it and then do it the other way. If x is a constant, so that means x squared is a constant here. What would be the antiderivative of e to the x squared times y if that x squared is considered a constant? Right. It would be 1 over x squared e to the x squared y. And then we have this, I'm sorry, x is a constant. Oh, whoa. We have all kinds of problems with this way. Because the thing is, y is our variable, and so we would have to do integration by parts. So you chose the hard way. Okay? Good for you.
But I didn't, because there's an x and y, it goes to e, and then x and y, so I didn't think there was like an easy order.
In this case, there is an easier way. We know that we can switch, when we just have numbers, we can switch the order of integration. So let's try working it like this. 0 to 2, we'll do the y last. On the inside, it's going to be 0 to 1 dx, and then we're integrating xy e to the x squared y. This inside one is going to be easier, I believe. Okay, y in the inside, y is a constant. Okay. Let's see, is this going to be, let's see here, y is a constant, well, how did I do this? Because that would then be, Yeah. Actually, I had to actually, before I even did anything, I just did a U substitution. Let U equals x squared times y. Did that come to mind at all to look at a U substitution? Always, 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 that's one of your principal tools in integrating is a U substitution. You always need to be open to that possibility, all right? So if that's our U substitution, now remember, y is a constant, so du is going to be 2xy dx, all right? And basically then we have xy dx already in our integrand. So 1/2 du, when I divide by 2, is equal to xy dx. And I think you should be able to go from there. Well, let's just figure out what your antiderivative is. Let's do the substitution. xy dx is going to be replaced by 1/2 du. E to the x squared y is going to be replaced by e to the u. So when you do your substitution correctly, you end up with a very simple item to integrate. So the antiderivative, of course, is 1/2 e to the u, right? And then we just get our variables back. So our antiderivative here is 1/2 e to the x squared y. That's our antiderivative of the inside. And then you go from there. Okay. I'm only going to take one more on the quiz because I've opened Pandora's box here, but that's okay. If there's anything else on the quiz.
Can we work with the other classes if we do that one?
Well, I'll see. It depends on how far we want to go. I'm not going to work the whole problem, unlike what I've been doing. Yes.
What happens to a balance in that case?
Oh, okay. Well, what I did was, Charles, you're saying what happens to the bound. Actually, what I did is I went back and put it back in terms of the original variables. So this antiderivative is this. So we have 1/2 e to the x squared y. And we're integrating from x equals 0 to x equals 1. Those are the bounds. I'm not changing my bounds.
Oh,
If I go back to my original variables, I can keep my original bounds. All right. Okay, then my bounds would be this. Okay, x is equal to 0. So that means u is equal to 0. 0 times y. Top one is x is equal to 1, so my top bound would be u is equal to y.
right.
Okay, yes.
Is there a general question about the very first one?
Oh, no, the very first one?
I did this problem like my mom figured out. And the second one, I got a negative answer.
Oh, yeah, they're both very different answers, yeah.
Okay, and it's possibly a negative answer.
Yeah, right. So, Cassandra's question is on the very first question on the take-home quiz. One of her answers for part A is probably a positive number, and the answer for part B is a negative number, very much different from the answer in part A. And her question was, can that be possible? And the answer is yes. Yeah. Okay. Well, the thing is, we're not looking at an area here. Actually, look at what we're integrating here. We're integrating y squared minus x squared. So definite integrals can have negative values. Okay. You're correct. Areas are never negative. Right.
I was just going to ask that because the first part A is the volume, but what is the measurement? What is it actually on?
Wait a minute. Yes, the first part for A is the volume? No. Wait a minute now. The first part, the only difference between these two parts is that I'm asking you to use different sample points in each of those little rectangles. Okay,
Oh, that's my area.
no, wait, no. If necessary, please review, I'm gonna lay this back at you. If necessary, please review section 15.1. All right?
Wait a minute, where, this is our test, this is two.
Duh, isn't that something? Isn't that interesting? Yes. Okay. I'm glad you caught on to that. Yes. The test is 15.2 to 15.10. All right. Okay. Let's go then to some review problems here. And I'm gonna... No, test is on Friday. Test is on Friday. It's a good way to start the weekend. Feeling that you have successfully done a calculus test. Excellent way to start. Oh, no. We don't even entertain those thoughts that can be an F or a D. Okay. Review set here. I need to get the book out too because so we know what these questions are. I thought I'd look at, first of all, and we'll just see how far we get with this thing. Number 4, it's section 15.3, it's at problem number 14. No, I'm looking at the review set. The review set. Let's see, this is on page 1074. All right. Okay, number 14. Aha. This is 15.3 number, and this is number 14. So the problem is 0 to 1, square root of y to 1, and then the integrand is y e to the x squared over x to the third, and then it's dx dy. And you're asked to evaluate this by reversing the order of integration. Yeah. Okay. Evaluate, but first change the order of integration. Now, the only way you can figure out your new limits is to draw a little picture. So here we're seeing, okay, what do we have here? Y, the outside, y is going from 0 to 1. On the inside, x is going from square root of y to the number 1. So let's figure what this looks like. X, let's see, what does x equal the square root of y look like? If I square both sides, that's x squared is equal to y. That's going to look like something like this, okay? And we're told that y just goes from, x just goes from this to the number 1, from this to the number 1. So this line here, this is x equaling the square root of y. And then the top limit for x is the number 1. All right. We're told that y goes from 0 at the bottom here to 1. This point right here, where is the point, let's see, x is equal to 1, y has to equal 1. So this is our region here that we're integrating over. So you first have to figure that out, otherwise you'll probably unsuccessfully reverse the order, because we have to change the limits. All right. So here, what we're wanting to start with dy. So we want to, instead of starting with x, we want to start with y. So we're going to go this way. Okay? Because before we were starting with x. Yeah.
So since we started with X first, originally it was going horizontal, right?
Yes, that's correct. As originally written, we would have been going this way with the horizontal arrow. But now because the reason we're switching is because you're not going to be able to figure out what the antiderivative is. Now we're going to be going with respect to y first, so we're going to be going with the vertical arrow. So let's figure out our limits of integration. Well, our lower limit for y is 0. Our upper limit is this curve here. Well, this curve is can be either written as x equals the square root of y, or if I square both sides, x squared is equal to y. So what would our upper limit of integration for y be? X squared. Okay, now let's put what we're integrating, y e to the x squared over x to the third power. That's our inside integral. Our outside integral, what are our limits of integration going to be for x? 0 to 1, right? Okay. So let's hope that we'll be able to have better luck with this way. So the inside integral is respect to y, so that means x is constant. All right. And notice here that pretty much the whole thing involves the variable x. X squared on the bottom, that's considered a constant. E is taken to the x squared power, that's a constant. So in a sense, this whole part of it is really a constant, all right? Our only variable in this is the variable y, so we have to keep our constant part as it is and integrate y. So we know integrating y, we're going to get y squared over 2, and then we just keep the rest of our constant stuff, e to the x squared over x squared. And so we were able to get an antiderivative, which is always nice, and now we apply our limits of integration. And then at the end, we'll do our integrating with respect to x. So let's see here. Let's plug in the limits of integration. Top one is y is equal to x squared. Oh, that's nice. So we have x squared e to the x squared over 2 times x squared. Oh, yes, you're right. Thank you. X to the 4th, because it's y squared. Y squared will be x to the 4th. Thanks, Cassandra. Wait a minute. What am I doing? The only thing.
Originally it was X.
Oh, was it? Did I change the problem? Let's see here. You're right. It's x to the 3rd, so I changed it to x squared. Way to go, Jim. Changed it to x squared, so let's do that. Okay, x to the cube. Nothing like changing the problem midway through. So, all right. So, and then our bottom limit is y equals 0, so we don't have anything. So let's rewrite this so it looks a little bit better. X to the 4th over x to the 3rd, that's going to leave me with an x, e to the x squared over 2. Okay. And now that's what we're going to integrate now with respect to x, right? So I'm going to pick on you. So Jenna, what technique am I going to use to evaluate this antiderivative? I use substitution. And what will be my u? U substitution, u equals x squared, and I'm going to leave it at that. We just go from there, all right? Well, let's not leave it at that. 2x dx, all right? So I can replace 1/2 du is equal to x dx. So what we have here then is x dx gets replaced by 1/2 du. I still have a 2 down here, so let me not drop the 2. E to the x squared is e to the u. And in fact here, Charles, I will look at, just do a change of my limits of integration. When x is 0, u is going to be 0. When x is 1, u is going to be 1 squared or 1. So basically this then becomes, I'm integrating from 0 to 1 of 1/4 e to the u du. So my antiderivative, of course, is just the same, 1/4 e to the u, and I apply my limits of integration. And I get what? 1/4 e minus 1/4 times 1. Okay. All right. Maybe, yes.
Or number 21.
Our number 15.4, number 21. I was going to do that one. Yeah. Let me go on and do that one. That was one of the ones I had circled. So what your question is?
I don't know how to get the limit.
Okay. All right. Why don't we do that one and then take a break? All right. So the question has to do, it's on the review set, and it's on section 15.4, number 21. Okay, so let me jam that on page 1074, number 21. So we're integrating double integral d of x squared plus y squared raised to the 3/2 power dA. And what are we told by d is it's in the first, we're told it's in the first quadrant. We're told it's bounded by the lines y equals 0 to y equals the square root of 3 times x. And it's bounded by the circle x squared plus y squared equals 9. All right. Okay. Okay, let's draw a picture here. We need to draw a picture of this d. First of all, let's draw the circle. X squared plus y squared equals 9. That's the circle of radius 3, centered at the origin. Oh, that's a good circle. So that's radius 3, all right? Now, it's in the first quadrant, so we know we're going to just be looking up here. And now y goes from 0, so here's y equals 0, to the y equals the square root of 3 times x. So basically, it's going to be, this is a straight line going out like this. Y equals the square root of 3 times x. Now, what is the slope of that line that I just drew? Right. M is equal to the square root of 3. Or we can look at it as the square root of 3 divided by 1. Okay. Let's see. Now, let's look at, so what we have to do here, this is going to go into polar coordinates. All right. So we know what our limit for theta is going to be, right? 0 to pi over 2. Because it's strictly the first quadrant. All right. No, that's, cross that out. This is our theta. We're talking about this area right here. Okay. This, of course, is theta equals 0. We need to figure out what is this angle right here. Well, basically, what we have here is we have the slope of this line is the square root of 3. So it's like, so the slope is the change in y over the change in x. So you can view this as a triangle where the vertical leg, say, is the square root of 3, and the horizontal leg is 1. So let's look at, I think we might have a triangle that works, right? 1, square root of 3, 2, that triangle, where this is 60 degrees and that's 30 degrees. So what would be our upper limit on theta in this case? It's this line right here. What would be this angle right there? That's marked by that line. It's pi over 3. Do you see by the fact that we've got that slope where it's square root of 3 up, 1 over, we can draw this triangle and get that angle.
So the slope always is the y over x.
Yes, slope is change of y over change in x. I'm going to just act like you didn't even ask that, all right? And I'm going to also assume that you knew from this right here that the slope of that line is the square root of 3. Okay? Y equals mx plus b. M is the slope of the line. So therefore, the upper limit is going to be theta equals pi over 3. All right? So what we have here then is what? What's our limit going to be for r? So theta is going to go from 0 to pi over 3. What about r? It's trapped within that circle. 0 to 3, right? Okay. So we said, let's see, let's do r first, 0 to 3. Theta is going to go on the outside from 0 to pi over 3. What are we integrating here? X squared plus y squared to the 3/2 power. Well, x squared plus y squared is the same as r squared, but be careful, we're raising it to the 3/2 power. And then we always put the r dr d theta behind it. What is that thing going to come out to be? That r squared raised to the 3/2 power. R cubed. You multiply the exponent, so this is r cubed. So we're integrating 0 to 3 r cubed times r, which is r to the 4th, dr d theta, 0 to pi over 3. Okay, and I think from there, this can be left right there. So you might have something like this, all right? You have to be able to figure out that upper limit of theta. Yeah.
When it's centered at the origin, r is usually the 0 and the radius.
Yes, right.
That was just different.
Right, that was different because in that problem we didn't just have a plain circle, because with a circle that's centered at the origin, if we're going out to the edges of the circle, that r is always going to equal a number, which is the radius of the circle. Yeah, yeah. Okay, why don't we take a 5-minute break?
You got my homework from your other school.
Yes, sir.
I had mixed class on both Friday and Monday because my street, like our training system was clogged.
Yeah.
and they weren't able to fix it until Monday, so I couldn't get out of my street because we had like a couple feet of water in our street. So here's my homework.
Oh, certainly, thank you. You know, this take-home quiz, you got that, and so,
Yeah.
so, I mean, this tells you here. You said take-home quiz.
Yeah.
Good to see you, I was wondering what had happened.
Okay, when you move in, it's just a determinant, right?
Yes,
And on this one, it's like a column of zeros except for one.
uh-huh.
So could I use this vector expansion?
Oh, since you're taking linear algebra, you can do that, that's fine.
Okay, I just
Right. I just showed one basic way to use the determinant, so that you know you can use any row, any column to develop it. That's fine. Yeah.
On that one, are you wanting us to set up a table, or do you want me to figure out what I did? I multiplied by r on both sides, and then it's like x squared plus y squared equals a squared. You want a table?
You don't need to talk. Okay. First of all, where do they meet? Yeah, 4 sine, theta equals 2, right? Right. Sine theta equals half, which is what, when the sine, I think that's pi over 3, right? Sine of pi over 3, pi over 6, sorry, pi over 6. Opposite, yeah. Right? Good. No, yeah, that's, yeah. Sine of 30 degrees is 1, or opposite over the hypotenuse. Yeah, it would be 1, root 3, 2. This is the pi over 6. Yeah. So, and they meet, that's one place that they meet. But wait a minute, we've got to have another place that they meet. So let's remember, all students take calculus. So another place that they would meet here, now you can do, what I think you might want to do is just do it, getting back to your question, you can do a table, you don't have to go to our x and y, it's rectangular. Just do a table with theta and r equaling sine of theta, and just do a few points. When theta is 0, this is going to be 0. When theta is pi over 2, this is going to be 4. Okay, when theta is pi, this is going to be back to 0 again. So basically, we start at 0. We're going to go up to 4 and down to 0. This is actually how this thing is. This is, yeah, it's as simple as that. You don't have to do a lot of points on your table. And of course, this is r equals 2. This is r equals 4 sine of theta. All right. And this helps you then. So we know that, so we're talking about inside this, but outside that. So we're talking about this, right? So once you draw the picture, inside this, but outside that. All right. So we have to figure out what are our limits of integration here for theta. We found out one place they meet here is pi over 6. The other one is going to be 5 pi over 6. All right. So we've got our limits for theta, pi over 6 to 5 pi over 6. That's for theta. Our limits for r, so that's theta. Our limits for r, what will our limits for r be? 2, right. 2 to 4 sine theta. And we're just looking at the area, so we don't put in anything here, and then we just do the r, dr, d theta. So actually, it's very, very, very helpful to do this part initially, so you have a visual on what you're working with, so you can actually shade in what you've got and go from there. near. You always want to see where they meet by solving that.
How do you like, have a point system? I was doing like pilot six and highway versus.
Well, I'm just using the basic, cardinal points there, and you get an idea. You know you've got these, so you know you start here, you're gonna go up to the 4, you know it's gonna be some kind of curvy line, and then it's gonna go from 4 back to 0. Again, you know it's gonna be a nice line, it's not gonna be anything else but that. And that alone, I think this alone, just those 3 points like that, very quick actually, you can see what this thing looks like.
It's like, right, so that's 3.5, what is that,
When you raise a power,
Is it multiply or add it for?
multiply. When you raise a power to a power, you multiply the exponent.
So this is just why it's there.
Yeah. Mm-hmm. Yeah. Let's see. What did I just do here? Oh, here. I'm going to copy this. Here, copy and paste. There. Whoops. That's just the stuff I attacked at the very beginning. All right, let's see here. What's the time left? What can we do next?
Or number
15.4, number 22. No, but I could do number 26. Why don't we look at number 26? This is on 15.4 still. So that's 15.4 is polar coordinates. Looking at number 26, because you were asking about 22. Let me get to. Choose some fish. Now, I'm going to say this. You were asking about number 22. Now, it's going between the circles x squared plus y squared equals 1 and x squared plus y squared equals 2. Now, I'm not going to do the... Huh? Wait a minute. Are you talking about... 22 on page 1026. Thanks. Thank you. All right. And I think this one... Okay, we'll set up this one. Let's set this one up then. This is number 22, and it's the one on page 1026. Again, it's 15.4. So this one is, we want to find the volume of the solid. And what we're given is this. It lies inside the sphere, x squared plus y squared equals plus z squared equals 16, and outside the cylinder, x squared plus y squared is equal to 4. Okay. All right, let's see here what we want to do with this. Okay. First of all, let's just kind of draw a picture of this thing. I really need to draw a 3-dimensional picture, not a 2-dimensional. X, Y, and Z. Okay, first of all, we've got the sphere. What's the radius of this sphere here? 4. It's 4. So the radius is 4. So it's going to be something. I'm terrible at drawing spheres also, but it's going to be this sphere radius 4. So it's inside that sphere, and it's outside the cylinder x squared plus y squared equals 4. So what also would be the diameter then of the slices of that cylinder? 2. So this is 4 right here. And then the cylinder then is going to have diameter 2, and it just goes up and down like this, vertically. All right. So it's going to meet, so here it is. It meets here, here. All right. So what we're talking about here is going from an upper, okay, we're going to do polar coordinates. In this case, this sphere goes down below. We have an upper Z and a lower Z. And we've looked at this before. Our sphere here is, so we're trying to figure out what this volume is that's outside the cylinder, inside the sphere. Our upper Z is going to be, well, Z squared is equal to 16 minus X squared minus Y squared. All I'm doing is isolating the Z. And then take the square root. Z is equal to plus or minus the square root of 16 minus X squared minus Y squared. So our upper Z is going to be the positive one, 16 minus X squared minus Y squared. Our lower Z is going to be the negative one. Right? So, we're going to do this with polar coordinates. What we're going to be integrating is the upper Z minus the lower Z to get this volume. So that's going to be the positive minus the negative. So I'm going to have a double negative again when I do the upper Z minus the lower Z. I'm going to come up with 2 times the square root of 16 minus X squared minus Y squared. Okay. Now I have to figure out what this region D is, and that's going to be on the XY plane. Well, hopefully we have an idea here. The cylinder on the XY plane gives us a circle of radius 2. The sphere on the XY plane gives us a circle of radius 4. So what I'm integrating here on D, theta is going to go all the way around to 0 to 2 pi. What's R going to go from? 2 to 4. So I have to set up my limits for R and theta, and then just do my upper minus my lower Z to get my volume. So let's just set this up here then. Jenna, does that make any sense? Okay, so let's set this up. So we're gonna do theta from 0 to 2 pi, R from 2 to 4. Now this is what we're integrating. 2 times the square root. Now I want to put this in polar coordinates. So how am I going to represent that inside the square root? 16 minus R squared, and then don't forget, I then tack on R dr d theta. So this is how the problem works out. And then what I use here is I use a U substitution, where U is equal to 16 minus R squared. and I can finish the problem with that. So therefore, du is minus 2r dr, and, yep, and so minus 1/2 du is equal to r dr. So I have 2 times minus 1/2, so I end up with minus, and then I have, this is the square root of u, when I do my du. Okay, is that going to work out? I think so. But it looks, something seems funny here with this. I think that's how, it should be how it works out. But, yeah, it's, mhm. Yeah, right, okay, right, exactly. Thanks. Yeah, I was concerned about the negative, but if we do look at the new limits for u, if we just plug them in here, when r is equal to 2, u is equal to 16 minus 4, so u is equal to 12. When r is equal to 4, then u is equal to 16 minus 16 is 0. So our limits then are from, are from 12 to 0, and we'll be okay as far as not having a negative value. All right, I don't really want to finish the rest of the problem, but that's how you set it up. Upper z minus lower z, figure out your bounds of integration for the r and theta. Let's look at this number 26 on the same section, and that's from page 1026. Same page. And here again, we're trying to find volume. And the region is bounded by z equaling 3x squared plus 3y squared, and z equals 4 minus x squared minus y squared. All right. Those are the bounds for z. Okay. It can help to draw a quick little diagram here of this thing. This top one, z equals 3 times x squared plus y squared, that's actually going to be a paraboloid type of thing where it's going to go up like this, that type of thing. This top one right here. The other one, 4 minus x squared minus y squared, that is going to start like this, and it's going to be a downward paraboloid like this. Okay. So we're talking about these two, we're talking about bounded by both of these, so we're talking about this area right in here that's trapped within both of those. Now, it's the same thing. First of all, we're going to have upper z minus lower z. So remember that. And then we have to figure out our bounds for theta and r. All right? And then it's going to be r dr d theta. Okay, the upper z is actually this one here. This is the upper one. So it's going to be 4 minus x squared minus y squared, upper z, minus the lower z, I'll put it in parentheses, 3x squared plus 3y squared, And I want to get this, of course, in polar coordinates. So this simplifies to 4 minus 4x squared minus 4y squared. Okay. So we can write this in polar coordinates how? 4 minus 4r squared. That's our upper minus our lower.
So are you doing that instead of doing your triple?
Yes, right, exactly. You could do the, so, Cassandra's question was, am I doing this instead of a triple integral? The answer is yes, although I could have done it as a triple integral, okay, using cylindrical coordinates, absolutely. But here I'm just doing the upper minus the lower z, and then just doing the polar coordinates. But either way would work, absolutely. Now, what are my bounds for theta and r here? Well, I've got to find out, these two are going to meet in this, basically it's going to be a circle here. So I have to look at where they meet. Because that's what I have to project down onto the xy plane. So we just take each one of these, 3x squared plus 3y squared, and I set it equal to the other z, 4 minus x squared minus y squared. And we just move all the x squares and y squares together over to the one side, and we get 4x squared plus 4y squared is equal to 4. And so divide by 4, we find that these things meet at a circle with radius 1. So by finding where they meet, see, this gets projected down onto the xy plane, and that is going to give me my limits for r and theta. So since it's a circle of radius 1, my theta, of course, is going to go from 0 to 2 pi. My r, though, is just going to go from 0 to 1, the radius of the circle. So what we have here, we have theta 0 to 2 pi, r 0 to 1. We have our upper z minus our lower z in polar coordinates. And I found that that was 4 minus 4r squared. And then we have to do our r dr d theta, like that. Distribute the r, and then go from there with doing the antiderivative. Can this thing be set, so this is going to be 4r minus 4r cubed. Can I separate this out into two single integrals? I can. If I have just numbers here for my limits, I can have the r stuff in one integral, the theta stuff in the other. So that's one single integral. The other one then is 0 to 1, 4r minus 4r cubed dr, and do it that way. Separate it out and multiply together. Let's see. Okay. Let's look, yes, question was about the spherical coordinates. Let's look at number 42 on page 1075. So, 42, page 1075. Number 42 on page 1075. This is under spherical coordinates. Okay, so here's the 42, page 1075. This is for section 15.9. All right, so this is what we're given, minus 2 to 2, 0 to the square root of 4 minus y squared, minus the square root of 4 minus x squared minus y squared, and plus the square root of 4 minus x squared minus y squared. And then what we're asked to integrate is y squared times the square root of x squared plus y squared plus z squared. And then this is dz, dy, dx. All right, dx, dy. All right. Okay. Let's first of all, let's just look in the xy plane. What we have here, we're told that y goes from -2 to +2, and x is going from 0 to square root of 4 minus y squared. So x is only in the positive, and this is going to be a half circle. This is x is equal to the square root of 4 minus y squared. So we see from that we're only doing a half circle here. That's one thing we can see. Now, all right. What this is here is this is basically here. This is let's look in 3 dimensions here. This is a sphere. This is the upper and lower parts of the sphere. Because we have, if we square both sides, we have z squared is equal to 4 minus x squared minus y squared. And so it's z squared plus x squared plus y squared equals 4. So my upper and lower limits for z, we're talking about a sphere of radius 2. Okay, radius 2. So let's just draw here 2. We're going to go 2 down. We're going to go 2 down, 2 across like this, radius 2. And notice here, and then this goes over this way, so we have x and y. All right. Okay, so what do we have to figure out? We have to figure out our limit. First of all, so we got to figure out limits for rho, limits for theta, and limits for phi. Now, rho is what we're integrating over. We're integrating within this sphere. All of this is within a sphere of radius 2. So my rho would go from what to what? Rho is distance from the origin. 0 to 2. Right? Now, theta is the angle that's made with the positive x-axis. Notice this is a little bit different here for theta, because here we're only working with this half of the circle. So I'm going from here up to here around the circle. So my limits would not be 0 to 2 pi. Yeah, you want to use negative pi over 2. It would be negative pi over 2 to the positive pi over 2. All right? The reason you don't want to use 3 pi over 2, you want it to go smoothly. If you use 3 pi over 2, then it will jump down when you get up to the upper. You want it to go smoothly from the minus pi over 2 to the pi over 2. All right? And then we have to figure out these limits for phi. Let's see. Phi then, or phi, that's the angle these points, any of these points make with the positive z-axis. But this thing goes all the way around. It's a sphere. So I can start with a 0 angle and go all the way downward to pi. All of those are included in what we're integrating over. So my c goes from 0 to pi. Right? Because c never goes to 2 pi. The maximum range of limits for phi, that angle with the z-axis, is 0 to pi. Here's our z-axis. For any point, we have an angle made with the positive z-axis. That angle is called phi in spherical coordinates. Let me go down and get the lower z-axis. The smallest this angle can be is 0. But we could go all the way down to have a point right down here where the biggest angle would be pi, 180 degrees. And that's it. It doesn't go any further. All right. Let's see here. So let's make sure we've got everything set up right. All right. So that's this is the hard part, is setting up the limits of integration. This is the hard part. So the rest of it isn't so bad. Okay. So we have here, let's put our theta. Theta is going from minus pi over 2 to pi over 2. Then let's do our phi. Phi is going from 0 to pi. And on the inside, we want to do our rho. It's going from 0 to 2. Now, yeah, it does. Let's see. In this case, because you're always going to have this factor rho squared sine of phi as what's called an integrating factor, you're going to pretty much always do rho, then phi, and then theta. All right. Okay. Well, what is it we're integrating? We're integrating this, y squared times the square root of x squared plus y squared plus z squared. So now I have to get that in spherical coordinates, because that's what we're working with. Now, folks, I do give you this hint on the test because there's a lot to memorize. I do tell you that y is equal to what? What's enough? I can remember. It's equal to rho sine of phi. This is actually the same as r, and since it's y, times the sine of theta. That's y, a rectangular y in spherical coordinates. I have a y squared here. So I'm going to have rho squared sine squared of phi sine squared of theta. I've got to square the y. Then, what is the square root of x squared plus y squared plus z squared going to be? That is rho, our distance. So we have rho, and then we then, don't forget, our integrating factor here, rho squared times sine of phi. And so this is d phi, d rho, d phi, d theta. This is the hard part, getting it set up with the limits. Okay, let's simplify that mess that I've got right there. I've got rho squared, so that's rho to the 4th power. I have a sine squared of phi, and I have just a sine of phi, so that's sine to the 3rd of phi. Oh, let's see here. Is it rho to the 5th power? Oh, yeah, 2. Whoa, what did I just do here? Rho. Oh,
formula.
That's right, I forgot that row right there, thank you. Yes, row to the 5th power. Then we have sine squared phi times sine, so that's sine cubed of phi, and then we have the sine squared of theta. All right. And this is going to go from 0 to 2 for d rho, and then I've got the other two out there that I have to do next.
Is there something that we can pull out?
Now at this point, let me write this whole thing then. So we have 0 to pi, and then minus pi over 2 to pi over 2. All right. So Cassandra is asking, can I split this thing up? And I can. As long as my limits of integration here are just plain numbers, I can get the theta stuff together, the phi stuff together, and the rho stuff together as 3 single integrals. So what would this be? Let's do the theta stuff, minus pi over 2 to pi over 2 sine squared theta d theta. That's my first one. My phi stuff is going to be from 0 to pi of sine cubed of phi d phi. And my rho stuff is 0 to 2 rho to the 5th d rho. All right. I want to look, what I want to look at are these two here, just to make sure we're okay. I expect you guys to remember this trig formula, this following pairs of trig formulas for the exam. Sine squared of theta is 1/2 times 1 minus the cosine of 2 theta. I expect you to know that. And its other one, its sister formula, so to speak, cosine squared of theta is equal to 1/2 times 1 plus cosine of 2 theta. I expect you guys to have that in your trig repertoire by this point in time. So this first integral here, sine squared of theta, I'm going to replace it with 1/2, 1 minus cosine of 2 theta. So this is going to be minus pi over 2 to pi over 2. So we're going to have 1/2 minus 1/2 cosine of 2 theta d theta. So antiderivative of the first one is going to be 1/2 theta. Okay, antiderivative of the negative cosine is going to be the negative sine. But what's my factor going to be in front here? What's my fraction going to be? 1/4. Remember, when you got that number multiplying in front, divide by that number, minus 1/4 sine of 2 theta is my antiderivative. And then you can always just do a quick spot check with the chain rule and see that, yeah, that works, okay? And then those limits go from minus pi over 2 to pi over 2. And I think okay, and then you just evaluate that. Let's look here, let me just look here at that middle one and just mention, we've already kind of mentioned this before. How would I handle that middle integral? Sine times sine squared, right? And then I'd write sine squared as 1 minus cosine squared, and I'd break it up, and I would use a u substitution for the second half of it. All right, let's just, this would be sine of phi minus sine phi cosine squared of phi. Well, I can figure out this antiderivative without any problem. For this part of it, my u needs to be what? This is cosine squared. No, I'm doing, no, wait a minute, hold on. I'm doing the middle one here. Sine cubed of sine cubed of phi. I'm breaking it up into the sine of phi times the sine squared. We did this at the beginning of class, so I represent sine squared as 1 minus the cosine squared. What would be just the use of here for the second one? Anybody? Yeah, cosine of phi. And then go from there. Okay? Yeah.
Well, for the first part, the sine squared, we use that 1/2 formula.
Mm-hmm.
And the other one for the sine squared, we use.
No, that's not sine squared. Whoa. Oh, for this one here? Well, it wouldn't do you any good. Let's say you wanted to try to use it. It won't do you any good. You'll find out that in this case, by replacing sine squared with this right here, you're not going to gain anything at all. I mean, you'll come up fighting for air, because you'll end up messing up, and it won't help you. Just work it out, see what you get, and you'll find you won't get anything. But by breaking this time, by breaking it up as 1 minus, because we know that the derivative of the cosine is going to be the negative sign. We can do a u substitution when we break it apart. Okay. All right. So that's the spherical one. I want to mention here on section 1510, that was that change of variables. The only thing that I'm going to have is doing a Jacobian. There's an example here. I would suggest doing a practice with this one, but we just know this is on section 1510. When we have 3 variables, what do we have in this case? We have x let's put it this way, f is a function of u, v, and w, y is another function of u, v, and w, z is another function of u, v, and w. When we have 3 variables like that and we want to calculate the Jacobian, we have to know how to do the determinant of a 3 by 3 matrix. So I did an example of that. Make sure that you know how to calculate determinant of a 3 by 3, and we know that this would be set up as we take our x and we do the partial with u, the partial with v, the partial with w, and then the next row we do our y with u, v, and w, and then on the third row we do our z with u, v, and w, and then once you have those individual elements, then do the determinant of it. On the what's that one? Let me look at. Maybe we have a chance just to squeeze this in. One thing. Okay. Since this comes up at a couple of times on the test, I want to make sure that I mention this. Let's look, I think the good place to do this would be just to look at number 39. This is under spherical coordinates. And this is at number 39 on page 1062. And I just at least want to get something set up with this because I want to make sure that you remember a certain fact. Wait a minute here. Is this number 30? Hold it. Yeah, it is this one, 39. What we're given here is we're given this. Didn't we do it? We did 42, yeah. Okay, this is what we're given. A triple integral from 0 to 1, then from 0 to the square root of 1 minus x squared, and then from the square root of x squared plus y squared to the square root of 2 minus x squared minus y squared, and then we're given xy, and then this is first of all dz, then dy, and then dx. And we're told to evaluate this using spherical coordinates. All right. Now, first of all, let's figure out what's going on the xy plane. X here is going, we're told, x is going from 0 to 1, and then y is going from 0 to the square root of 1 minus x squared. So this time around, this is a little bit different than the previous problem we had. This again is a half circle, but now it's on the upper half plane. Okay, so this is what we have. Now, we have to figure out our limits of integration for rho, our limits of integration for theta, and for phi. Let's see what this thing kind of looks like. So z is going from the square root of x squared plus y squared. This is a cone, like this. Z equaling the square root of x squared plus y squared. That's the lower part. The upper part is a sphere. This upper z equaling the square root of 2 minus x squared minus y squared. If I square both sides, it's z squared equals 2 minus x squared minus y squared. So we see if I add the x squared plus y squared, what we see is the upper part is a sphere of what radius? Square root of 2. Radius, square root of 2. So basically, our upper part starts wherever the square root of 2, 1.4, and goes down like this as the sphere. Okay. All right. So what we're integrating over is we're just integrating over, this is our x, this is our y. We're just integrating over this part on the xy plane, and then between these two parts here on the z plane. Now, let's actually start with theta. What would be our limits of integration for theta here, since we're only looking at the upper half? 0 to pi, right? Theta is going to be from 0 to pi because of this reason right here. Now, rho is going to be from the origin all the way out here to the boundary of that sphere. All right? So what's the maximum distance there for rho? It's the square root of 2. It's the radius of the sphere. So it goes from 0 to the square root of 2. That's the radius of the sphere.
For rho, if x is limited to 0 to 1,
Mm-hmm.
would theta be 0 to pi over 2, or is it 0
Oh, wait a minute. What do we have here? X? What do we got here? X is going from, wait a minute. Oh, you know what? Yeah, you're right. I just completely ignored that. X is going from 0 to 1, right? And y is, so actually we have a quarter circle here. Thank you. We have a quarter circle, right. So our theta here is going from 0 to pi over 2. Yes. Okay. And I can tell you this problem's harder than what you're going to see on Friday. All right. So we only have a quarter circle here. Much thanks to you on that. Okay, so that's our theta. Our rho goes from 0 to the edge of the sphere. Now this is the thing I really wanted to emphasize here on this one. When this boundary here of a cone, where it's z equals the square root of x squared plus y squared, when we're talking about phi, we're talking about an angle from the positive z-axis. This thing here, this whole boundary here, its angle from the positive z-axis is pi over 4. No, not yet. So, this is what I want you to remember. That for this cone here, z equals x squared plus y squared, we can represent this in spherical coordinates as a very simple equation, phi equaling pi over 4. So remember that when you have this kind of cone here, that's here, your phi, it depends on whether we're looking at the upper part or the lower part. Here, phi is going from 0, we want to go all the way upper, to the pi over 4. All right? So I want you not to be left in the lurch about what that one limit of integration is for phi when you're dealing with that kind of a cone. Z equals the square root of x squared plus y squared. All right. Jenna? Why don't you ask me after class? No, actually this all fits together. Within this, your x will be, you won't, okay, I see what you're saying. You're saying, well, this all looks like it's outside the cone. But when you're doing these spherical coordinates are not the same as rectangular coordinates. We're looking at these three variables here. We're looking at all these points right here, but we're looking at them in different ways. We're looking at them as what angle, when we drop it down, what angle does it make with the x-axis? And that gives us our theta. So don't think of it the fact that, x, that's outside of my region. Don't look at it that way. We drop it down and we look at the angle that's made with the positive x-axis, and that gives us the theta. That's why it's very helpful to draw this two-dimensional diagram if you're confused about what your limits are for theta. The theta is going to be in the xy plane. All right, and that's it. We're out of time. Feel free to email me with any questions. And there's a bonus question. That's always nice.